Thank you, Steve. We'll do the handshake and then. Hi, everybody. Yeah, as Steve said, our research group focuses on the future of AI, how it might be used across our various industries, manufacturing, construction, and media and entertainment. And as you can probably likely imagine, my life has been incredibly busy for the last 4 or 5 years. And it's only getting busier. So I thought, when Bruce and folks reached out to us about this conference, I thought what would be really useful is to show you a mixture. I want to show you what we're putting into market, what kind of AI things are coming out, and how people are beginning to use those. But I also want to show you what's coming next. Because the reality is, as we all know, this stuff is coming on fast. And what you're seeing is next today is going to hit you in 6 months from now. So I think if you're in a decision-making capacity, if you're thinking about this stuff, never has it been more necessary to really stay on the bleeding edge of kind of where AI is going and how it's impacting your industry. So with that, what I want to start off with, I want to just address something straight off the bat. This notion that the sort of AI replacement theory, my goodness, AI is coming, we're going to have a big green button, we're going to press it, it's going to make the thing, and you're done, everything's going to be automated, the robots are going to do everything. There's just so much hype that we're all dealing with all the time in this industry. I'm not a proponent of replacement. I think the problems we all deal with in this room and the physical things are actually too complicated for that. I think there's a human factor that's so intrinsic in these things. And for those of us that are working in this space, we really need to figure this out. We really need to how to build these AIs, build the interfaces so that we can create, rather than a replacement, a harmonization. And I really do believe this is the sort of core premise, if you want, that I'm going to leave you with today, is that I do believe if we do this right, we can find the way to build a sort of a harmonious approach to really build the tools in a way that we can leverage them to their full capacity and really change the world fundamentally. So with that, if you go online and you go and search for AI, deep networks, at some point you're going to find an image that looks like that, right? And obviously the signal there as well. Deep learning networks are kind of like a human brain. They think like a human brain. Well, I'm here to tell you, nothing can be further from the truth, right? The reality is these deep networks that we're working with in AI are brilliant. They're incredible, but they're fundamentally different from the way a human brain works. They don't think and reason in the same way that we do. It's not a form of thinking that we're typically used to, right? So what do we mean by that? Well, I mean, humans fundamentally excel at sort of context. We understand social connection. We actually happen to be very, very efficient learners. We understand the human place in things. We're really, really, really good at understanding the context. So we bring that. On the other hand, these systems, when they come along, they're incredibly good at bringing massive amounts of data together, finding these patterns, and they can be really higher order patterns in this data, reacting to those. They can do things at speeds of calculation that we obviously cannot do either. So when you actually put these sort of two things together, these two sides of it are actually quite different, but they're actually very complementary. And this brings me back to my harmonization argument, that these are things that actually, although they're different, there's an opportunity for harmony. Now, I've said that they're different. There's actually a similarity that exists between these as well. As you all know here, the human brain divides our reasoning into different areas of our brain. There's occipital lobes, neocortexes, there's all these different parietal lobes, these different areas of our brain that work together in various patterns to accomplish the capabilities that we have as human beings. Now, it turns out that the large AI models are starting to do the same thing. When you look at across these AI models, there's mixture of experts models, there's agent networks, there's various ways of coupling models together, co-conditioning models. This is happening more and more and more. And as we're moving past this era of sort of large language models and vision models, and we're starting to look at the world more broadly and try to do more things, we're beginning to realize that the only way to achieve this is through systems of specialization. And when these systems of specialization start to mesh together, then you can start doing kind of higher order things like we do as human beings. So that's interesting. There is a similarity. Now, of course, as you see on the slide here, when you put these two things together, human beings are still doing pretty well, right? Language models models are excelling at a small number of things right now. Vision models, language models are really good at these things. There's a bunch of other stuff there that is still really, really, really difficult for these models to get going. And I want to hone in on those top two around input and spatial. We're going to talk quite a lot more about those. So with that, I mean, if you think about input and spatial reasoning, human brains have been developing, evolving for hundreds of thousands of years. The limbic system in our brain is actually nearly, I believe it's about 10 times denser than our neocortex in our brain. So there's a longer amount of evolution that's gone behind the development of these systems. So that's why, people like Moravec, Moravec's paradox, that, things that are hard for humans is really easy for machines, and things that are easier for humans turns out to be really, really hard for machines, right? So, I think it was Minsky said, I can't remember his exact quote, but I think it was something along the lines of, we are least aware of the things that come most naturally sort of to us. And I think that's becoming very, very obvious right now in this work. So this is the sort of origin of that difference. So, what machines lack is fundamentally this ability to learn the physical world. When this little baby is here and fiddling with blocks and finding weights of things and learning how things feel and textures and all that, there's no reward function like in a reinforcement learning model. There's no data processing. It's an experiential loop that's coded into us to start discovering the world and encoding these things. We're still a fair way away from that in AI, is the reality. I mean, it's getting closer, there's no doubt about it, but we're still a fair way away from it. And this is one of those missing systems, one of those missing ingredients on the other side of the equation that I talked about before, right? Now, the reality is, if we don't solve those things, these, solving things in the real world in which we all exist is going to remain out of our reach. And I often use as an analogy I use in a lot of my talks, simple analogy. It's 3 a.m. in the morning. You wake up and there's a sound of water running in your house. Oh, that's not good. There's water pouring through the roof. What are you going to do? You've got two numbers to phone. They're both plumbers. One is a plumber that has read every single book on plumbing in the world. They've watched every video. They've never touched a pipe ever in their life, but they've read everything and they've memorized it as well, which is really cool. The second person is a plumber who's done plumbing for 30 years, barely reads, but has got 30 years of actual plumbing experience. I know which number you're all going to call. It's probably the same number I'm going to call, right? It's a simple analogy, but it's a little bit similar to how VLMs are functioning today. They know enough to get you dangerously far down the line, but if you really want to start closing the gap and actually solving the problems, you need to bring in this physical experience. It's an absolutely essential ingredient. So, and again, with all the hype we're all dealing with, we have these moments where people point out that, vision language models don't understand clocks. They don't understand time. You notice that? They don't understand time. So, there's a gotcha. They're terrible. These systems are fundamentally bad. They're not fundamentally bad. They're actually, they're beyond belief good at what they do. But they don't understand things again about the physical world. And it turns out that clocks and time is actually one of those physical things that doesn't really fit into the nature of those models, so it doesn't pick it up. So, we have to figure out ways that we can start gathering information from the physical world. We can start experiencing that physical world, and we can start modeling that physical world. And this is difficult because vision language models, as you all know here, were trained on the vast trove of data on the internet, images and language, of which there's almost not quite limitless supply. We're now probably at the limit nearly, but there's an enormous amount of it to get you going. The real world is a heck of a lot more complicated. There's a lot more data, and it's much harder to get to. In some cases, it's really, really difficult to get to or measure in any reasonable quantitative sort of way. So finding ways to do this is really tricky. And this is an area where our lab, when we set up our AI lab in 2018, this was the core focus, because we were noticing that very few people in 2018 were working on this thing. If any of you in AI here, wind your brain back to 2018, you remember everybody was super excited about the Twitter feed data set. That's what everybody was working on in 2018, right? So they were very, very, very narrowly focused, and we recognized that we've got to start working. We looked for partners, and there was very few partners. These days, MIT CSAIL here is one of our partners. We have a lot more today, but back in 2018, there was very, very few people working on this sort of physical AI. So, a lot of the basis of my talk today is going to be about physical AI, and how does physical AI actually going to change the way you work, and how's it ultimately going to create this harmonization that we spoke about in the beginning. So our AI lab had well over 100 AI research papers in this field. We're the leading publisher in the world right now on physical AI for CAD in this space. Like I say, we've been spending a bunch of years really going very, very deep on this and trying to figure out the right ways to do this. And I'm happy to say, with a lot of investment over the last 5 years, this has started to roll out into our products. And this is some of the stuff I'm going to show you today. So the core work that we've been doing is something that we term neural CAD. So neural CAD is really a set of foundation models that we've been training on spatial concepts, geometric concepts, systems, structures, and physics. So it's looking at all these kinds of data. And again, we don't have all of the data for these things, so it's still the early stages of it, but this is what we've been working on. So I'm going to show you first a very practical example of this. So the first version of neural CAD came out actually at the very beginning of next year. We didn't announce it to the world at the time because we didn't actually know how this is going to work. And this is one of the difficulties of AI. When you're developing these AI, you don't know how they're actually going to practice in the real world. When people throw actual problems at you, you sort of discover it kind of as you go. So we kind of slid it a bit under the radar. And the first problem we took on was sketch constraints. Who here has worked with constraints? Who's built constraints? Okay, now who liked working with constraints? Okay, well, you're strange. I don't know. We'll talk afterwards. But, the reality is, go back. The reality is that, constraints are difficult, right? And, when a lot of people that don't know much about CAD think CAD is just about making a shape. CAD is not about making a shape. CAD is about explaining the intent of how you want something to behave. It is really giving you, it's got a timer on the slide. It's really about explaining all the nuances. So that little circle, an under constrained sketch, if you go and you change the dimensions of one of the arcs, it all of a sudden bubbles. Obviously, you wouldn't want that in that kind of shape, likely. So the thing that made it do that, or not do that down below, was a set of constraints, a set of rules that said, if you change that one dimension, here's how the other dimension is going to change relative to that. Turns out this is one of the most common areas of mistakes. Like I said, most people don't like doing this, but it's even worse than that. They keep making mistakes in this. And what often happens is you'll have something like, for example, a collinearity constraint, where you've got two lines, and you think you want to make those two lines perfectly collinear. What a lot of users do is they move those two lines to they look perfectly collinear on their display, and they go, okay, I'm done. Except when that ultimately gets extruded and it goes to a piece of metal and it's now in manufacturing, and the mill, every time it comes to that, goes and it makes a weird little line. And everybody's going, why the heck is the mill constantly making this little line? Turns out it was months ago when somebody didn't get the collinearity constraint right. So it can cause, like a tiny, tiny, tiny little thing like that can cause major downstream problems. So we trained our foundation model to do constraints. It basically looked at all of the patterns of constraints. So here you can see a shape. Somebody put in the shape. You hit auto constraint, and there's a bunch of constraint solutions for you on the right. You can choose which one you want. You can choose of multiples. Sometimes there's multiple ways you could constrain something. And then there's even a slider. You can see there's a modified geometry slider over there. So what that is about is it's about kind of setting your threshold. So some of the constraints it's very certain of, like it's almost certain that this is a good constraint. But there's other constraints that are like, well, I think it's probably a constraint you want, but it may be not. So you can think of it as similar to temperature that you get in other AI models. You can sort of set that threshold, and then it'll filter out some of the things that maybe you don't want. So we've seen massive uptake. So this is not a world model. This is not creating anything enormous. This is not, solving complicated physics problems or anything, but it's solving a very practical, very real problem that people have. And we've seen people go from spending days getting complex constraints working across multiple bodies in an assembly to getting this done in, 15 minutes. And it's valid. So there's less errors, you speeded things up. So this started giving us some very good signals. And I'll be honest, the very first model we put out wasn't brilliant. The first model we put out, it was better than nothing. It was, there was still a fair amount of errors. We managed to get a bunch of feedback on this. We started post-training the model. By the end of the year, we'd increased its accuracy by 75%. So now it's excellent. So again, this is the thing, because we saw the patterns of how people were actually using constraints and how this. So very practical example, very focused, but this is what gave us the confidence that we knew that we could keep building out our foundation models. So here's another a very quick example of a shape search system. We've done an embedding system. We've got one of the world's largest embedding models. So this is something that basically codes shape, but it doesn't code shape just from a 3D perspective. It codes shape from a 2D perspective as well. So if it sees a picture of something, it understands that that's equivalent to the 3D thing that it matches to as well. This is a very, very large model trained on an enormous amount of content. But what we did with this one is what you're seeing here is actually a customer tool. This is not something we built. We released it as an API, so it can be built into people's workflows, because we recognize that with something like shape matching is an opportunity for people to build different workflows. What about something that automatically builds your bill of materials because it understands components and it can actually categorize components based on position, shape, things like that, right? So you could break through, you could understand, if you don't have a part number on something, it could automatically assign part numbers. You can make all sorts of things around it. So we found a whole bunch of people beginning to use this as a sort of a base part of our platform. We're rolling it into the software as well. You're going to see more of that coming later this year. But now let me get to some of the more advanced stuff. So now at Autodesk University last year, I launched NeuralCAD for geometry. So this is our feature coming out in Fusion fairly soon, where you can come in and just prompt 3D things into existence, right? So here you're seeing I'm prompting a bunch of different shapes, different kind of consumer products. So we're starting more on the sort of conceptual design. So imagine I'm a designer of a power drill. I can come in here, I can type drill, and it'll start synthesizing, in this case, 9 different models of a drill for me. But now what you're seeing is not just a special effect. What you're actually seeing is literally how the AI actually functions. It predicts surfaces, it predicts cut edges, it predicts shapes. So those dots that are coming in are actually the curvatures of the surface and the vertices coming in. But the important thing is what it's actually producing here is first-class actual CAD geometry. This is not a mesh. This is not actually a point cloud. This is actually editable CAD geometry that it's creating directly, one shot from what you're asking it for. Now, that's all really well and fine, but I'm sure any designer in this room is going, okay, great, I love that you can prompt something, but I actually want to control it because I'm actually a designer and that's actually what I do. So the great thing is with one click now, you can be inside Fusion. And now let's say I want to add a handle on the side of this drill. I specify the exact content point, it has to be that exact dimension. I specify where I want it to connect. And now I go into the AI software and I want to put a handle. So what I do is I just draw the handle. Okay, give it an outline. And again, this is where we're going past the harmonization I spoke about before, going beyond prompts. I say synthesize it, and it starts synthesizing the exact geometry that connects to that the exact point I specified, plus honoring the rough shape that I drew. Not only that, but if you actually look at the history sequence inside Fusion of what's there, there's actually a full sequence of the history of creating that geometry. So it didn't just create a boundary, it actually created the CAD operations that created that. So it looks like it was created by a human. And this is an incredibly important learning. In all of our research and development work, if you don't build AI that gives the human full control all the way to the bottom, it's useless because the AI is not going to get it right all the time, and the human's always going to have underspecified something. There's going to be something else they want to do. So providing them that level of control is essential. Okay, so from there, we went on to another team, started working on buildings. Now, I know I'm in a room here of manufacturing folks, so I'll go quickly through this. But the reason I'm showing you the building one is because buildings are very complicated systems. The building we're in right now has heating systems, plumbing systems, electrical systems, there's structural plans, there's general contractor plans, there's all sorts of things going on. So what we did is we built NeuralCAD for buildings as well. So this is intrinsically trained on the systems that exist inside buildings. Now, buildings have like I said, there's all these interconnected systems. So what we decided is, here you're seeing somebody take what's called a massing model of a building. It's the very simple early conceptual stage of a building when you're simply shaping out a building. And what it's doing is it's predicting all the internal structure of that building, where elevator cores are going to go, stairwells, corridors, rooms, all of this kind of thing. So you can actually immediately predict, just create the box of the building, and it's just going to run through and create all the fenestration. It's going to create columns. It's going to create everything for you. Now, the great thing, again, is you want control. So here, an architect has come in and said, I like what you've generated, lock down this corridor in these 2 rooms, but I'm now going to use prompting to tell you about a new kind of material that I want to use. I want you to use a different kind of concrete in the building. That different kind of concrete's got different loading characteristics. So because of those different loading characteristics, it's going to calculate a different layout of the building. But it's going to lock down that corridor in those rooms because he really likes that specific layout. So you'll see there some columns have appeared. Notice the thicker columns on the outside. That's all due to the material changes in this building. All right, so with that, just wanted to give you an idea that, this kind of thing is happening across industries. That same systems approach is also beginning to roll out in the manufacturing space. And at a future talk, I can tell you more about how that's going to impact thinking at a sort of a systems level, at a full assembly level, when we're dealing with mechatronics and things like this. All right, so we've got neural CAD. So this is where we're at right now. We're rapidly evolving these CAD models, these large models. But what really, to make these things really work, and you saw it with the sketching of the handle, we really have to start changing our relationship with machines. Because if we've got these incredibly smart models, but they're not actually able to react to us correctly, we're not going to fully leverage them. So I'm going to show you here a quick research demo. This is not a product yet. This is from our research department.
It's actually supposed to be a perfect cuboid.
Notice that as he said it, it became an actual
let's
cube.
Add a really grand.
So you're getting input
like an arch shape
from sketch and voice at the same time.
It's actually a church building, so let's add a cross here.
No, he didn't actually draw a cross, but a cross appeared on top of the.
Let's surround
right
the building
again. So
with,
there's things that we can
base,
explain very
series,
easily with language, and there's things we
here's
can
a set of
explain very
staircases
easily with
leading up to
sketch.
the entrance.
And they're actually quite complementary. So why not do both
Well,
at the
actually,
same
fewer
time?
steps
And we're
in the
finding if the
staircase.
AI is responsive enough, it actually feels incredibly
Maybe
natural.
like
In fact,
4
the learning
steps.
curve of software goes to nearly zero if this is how you work. So I strongly believe this is the future of how we're going to interact with these models. Here's another example of where we didn't do voice, but we took annotations as far as we could take it. So imagine if you're drawing out this little cabin over here. Again, you draw out the shape. But now you start using annotation. First, I'm going to use a prompt. I'm going to set it, what I'm making, so it produces a better version. But now I'm going to start drawing on top of it. And I'm going to write literally what I want to do. And the AI is constantly interpreting. Every single time I do something, it's interpreting what I'm writing, where my arrows go, the spacing, where I want the shrubbery, and it's just naturally synthesizing constantly. What's more natural, right, than simply just drawing and writing and having the AI constantly respond to you? So I wanted to show you those examples, because I think if we get this right, this relationship, this sort of similarity that we talked about on the sort of spatial and the sort of input side, this radically starts to exercise this sort of harmonization that we talked about. And I think this is where AI is going to really, really come in useful. It's not just putting in a prompt and hoping that I'm going to get the right thing. It's this sort of interactive pattern. Now, this is what I truly believe this is the future. I'm very excited about this. I've got dozens of researchers and engineers working on these very specific things, because we believe this is the future of all industries, of how we're going to interact with AI. I went backwards. Sorry, let's go on forward. Now, design is, I'm not telling you anything new in this room. It is one of the most complicated things we do with computers. If you want to learn Maya, like a product like Maya, it takes a month to become even basically proficient at Maya. This design, if we can get this right in design, we're going to get it right for all software. Design is going to be the sort of harbinger of how software is going to be defined in the future. But with that, there's another problem that we have to solve. We have to start understanding the world itself. Now, some of you may know this. A few months ago, Autodesk did a very large investment in World Labs. World Labs is Fei-Fei Li's new company building a world model called Marble. Now, just to give you, for those of you that are not familiar with world models, I think you all know that at the core of a language model is effectively a system that is predicting the next token or the next word in a sequence, and then it's scaled up in very exotic ways. Well, a world model is similar in that it's trying to predict the next state of a world. Given the current state, it's trying to learn how it can predict the next state of the world. Obviously, that's a lot harder because it's, well, the world we're dealing with. So I'll give you a little quick bit of their demo. They've got a nice flashy demo. We can just watch a little bit. We don't have a lot of time. But I mean, they're building some incredible technology that's trained on video. It's trained on large amounts of content to imagine a world and be able to allow people to simply just create through prompting, through sketching, through whatever. And it actually is persistent. And actually, all of the content in this video that you're seeing, the 3D content, is all created in their world. So that her experience of walking through this environment, the different effects, that is all created in Marble. And if she changed something and she walked back into a room later on, it'll remain changed. So there's persistence in the world. It actually understands it. So this is very, very exciting technology. It's got a long way to go. We're at the we're not even at the GPT 1.0 moment of world models yet, but I do believe it is the right place sort of to go with this. Now, with that, at the same time, what we're doing inside Autodesk is we are doing a lot of work at the very fine-grained physics level. So this is just two examples from our lab. The one is a manifold from a jet engine where we used a simulator, an AI-based simulator to do all the fluid dynamics kind of calculations in real time through this thing and try out multiple scenarios and then optimize the shape of this because we could actually run the simulation in a loop far faster than we were able to do. So in other words, it's a topology optimization problem. On the right is a real-time contact physics system for robotic grippers. So this is actually a system that designs entire mechanical assemblies because it can actually predict the contact physics of what's sort of going on in there. So you can almost imagine we're coming to this from different sides. The World Labs guys are looking at the full picture. We're looking at it kind of from the other end. And then the last thing I'll just share with you as we wrap up here is here's another example of using real-world physics. This was a project to close the gap between simulators that predict what the real world's going to look like and what actually happens in the real world. So it turns out if you put a lot of sensors on these things, you can collect enough data and you can start training a system that gives you an actual specific real-time simulator for just, in this case, this drone. We then took that, we brought it back in, and we were able to redesign the drone based on exactly the measurements of what actually happened with this drone in reality. So in other words, you get this one-off simulator each time. And then the last thing is, the other thing we're doing is we're applying this to robotics. Here's a Stewart platform. Some of you may have worked with Stewart platforms, effectively the simplest robot you can have out there. Also a very difficult thing to assemble. That was actually our AI predicting the assembly sequence. And here's a robot actually in our lab doing full closed loop adaptive assembly of a Stewart platform with multiple arms. This is all driven again by the same AI-based physics systems. It's using a vision language loop. It's using vision tactile loops. So it's got force sensors on it as well, working on collaborative regrasping and placement. And if you've ever tried to assemble a Stewart platform, even human beings struggle with doing this, by the way. It's got these very complicated, weird things that you have to hold. You often run out of arms when you're trying to make something like this. So it's pretty cool. So again, a long way to go. I do believe that robotics is going to go through a revolution as well. I know we have some talks on this later today on this. I think this is driven by the same kind of trend. So this is really exciting. But anyway, hopefully this gives you all a sense of sort of where all of this is going in the future. There's some more videos there. Hopefully this gives you a sense of where all of this is going. It's real. We have a long way to go still. But this future of harmonization, of how humans and machines are actually going to work together is absolutely critical. And all of us need to work on this together. We all need to demand more from the software, react less to the hype that's out there. We're not going to design everything through a prompt. Prompting will be part of it, I'm sure, but there's much better ways to actually, really realize that complementarity that exists between us and the machine. Thank you very much.
Right. Thank you, Mike. Thanks. Yeah.